Okay, so this is Math108 Trigonometry, lecture number 1. First topic we'll talk about would be essentially a review of concepts you picked up from algebra, principally Math 107. So we're going to start off with a brief discourse on functions. Okay, so definition. A function f, okay, is a rule that assigns to each element x from a set V exactly one element f of x from a set C. Okay. So, for instance, consider this. F of x is equal to 1 divided by x plus 1. All right? So this would be an example of a rational function. Now, we're going to be talking quite a bit about rational functions in this class. And so one of the things we are always on the lookout for when dealing with rational functions would be the domains of rational functions. So in this case, we have the domain. The domain is equal to what? X, set x such that x cannot equal to -1, right? So here I've listed the domain of f of x in roster notation. So we have types of functions, different various and sundry types of functions. First type would be special functions. Okay, and one of the more common special functions would be the absolute value function. So let's discuss the absolute value function, a function that we'll probably be using quite a bit in this class. So absolute value of x is a piecewise defined function. Okay? Written thusly, absolute value of x. So what is the absolute value of x? All right, so absolute value of x defined piecewise is equal to the following. It's equal to x if what? Can you answer this? If x is greater than or equal to 0. Okay? So, for instance, the absolute value of 9 is 9. The absolute value of 3.14159 is, of course, 3.14159. Now, if x were less than 0, then the absolute value of x is equal to the negative of x. Okay, so if x is less than 0. All right, so this is the definition of the absolute value of x. So, for instance, if x is -5, then the absolute value of -5 is 5, because minus 5 is 5. So, please be mindful of this definition. And there's also an alternate definition for the absolute value of a number, and it can be written like this. The square root of x squared is also another definition of the absolute value. All right, so that's one example. Another example of types of functions we'll be processing in this class would be trig functions, which is what most of this class is all about. So trigonometric functions. So we'll have more on this later. We'll start talking extensively about this topic in Chapter 2. Third class of functions we'll be dealing with would be exponential functions. All right, so what are some examples of exponential functions? Well, the generalized exponential function is written how? Let's see. Generalized exponential function would be written as y equals what? A to the x, where your variable is x and a is the base. Okay, so an example of a common exponential function that we'll deal with quite a bit would be the exponential function. So the exponential function is y is equal to what? E to the x, where what is e? Okay, do you recall what e is? Okay, so if you don't remember, e is equal to 2.71828. Now e is an irrational number, so what I've written here is an approximation to e. Okay, so what next? Exponential functions. Oh, polynomial functions are another class of functions that we'll be talking about. So let me write that down as a fourth class of functions. Polynomial functions. Okay, so an example of a polynomial function would be a quadratic, right? So quadratic function. Y is equal to what? Ax squared plus bx plus c. Okay, so this would be an example of a quadratic equation. Okay, so the quadratic equation. The quadratic is in fact a special case of a polynomial function. And then a fifth class of functions that we'll be working with would be the so-called rational functions, which was like this first example that I showed you. So let me write that down for you. And the generalized format of a rational function. Okay, so rational functions. Okay, so a rational function is written as a ratio of two polynomials. Y is equal to p of x divided by q of x. Okay, so this will be the generalized notation. And of course, with the understanding that q of x does not equal to 0, right? 0, okay. So this would be the rational functions. Okay, so let's do a review of how we deal with, say, parabolas. One of the things we're going to be dealing with extensively in this class is graphing functions. So we can start off by reviewing concepts of graphing. So let's say we want to graph a quadratic. F is equal to minus 2x squared minus 5x plus 3. Okay, so we want to graph this function. That's our objective. We want to graph this function. So we start off by considering, where does this graph exist? Well, since this graph is a polynomial, note that polynomials exist on the entire x-axis. So there are no restrictions. So you can think of any number, plug it into the polynomial, and you'll get a number as an output. Okay, so that means what we're essentially saying is the domain, that is the set of allowed inputs for f of x is the set of real numbers. Okay. Likewise, the range, that is the set of outputs. Now, I readily admit, okay, one note, I readily admit that I'm going to have a lot of typos in my lecture notes. So if you see a typo, you can attempt to correct it, or if you're unable to understand the meaning of my typo, just send me an email and I will clarify it. I'll put a note in, on the class website clarifying what the typos are. So, but as I go through the lecture notes, you're going to see a lot of mistakes. Feel free to contact me regarding the resolution of mistakes. Okay, so like right here, for instance, I just made a typo. But anyhow, let's move forward. All right. So the range is the set of outputs of the function. Okay. So likewise, the range, which is the set of outputs of the function, is again the set of real numbers for this function. Okay. So there I go again, typing mistakes. Okay, so we have the domain and the range, and of course, the only time domain and range issues become things that you have to really consider would be dealing with rational functions or special functions. Another notation I want to demonstrate is the symbol for the set of real numbers, and it's this. This symbol I'll use a lot for the set of real numbers. Set of real numbers. Okay, so if you see this R with a double backbone, that means the set of real numbers. All right, so where were we? Oh, so now we are going to graph this function or review the structure of this particular function. Okay, so one of the things in graphing this function is we need to know what the x-intercepts are. So x-intercepts. Now what are x-intercepts? Okay, where the graph crosses the x-axis. In other words, these are the roots of the function. So how do we find the roots of this quadratic? There are a couple of ways. Well, two ways in particular. One way is we can factor it. So if we factor it, and I'm going to presume in this class that you're fairly competent in factoring polynomials. If not, please do so in a hurry. I have my algebra Math107 notes posted on my class website, so you can look up some of the techniques there, consult with the tutor, or just go online and take a hurried refresher of factoring. The factoring won't be as nearly draconian as it was perhaps in 107, but still, nevertheless, it's an expected skill I'm looking forward to your having. All right. So anyway, if we were to factor this polynomial, it would be something like this. F of x is equal to minus 2x plus 1 times x plus 3. And if you need convincing that this is the factorization, just use the FOIL to check the answer. So if we do it this way, then it readily follows that we can get the x-intercepts from this by simply setting each of the prime factors, these two factors, equal to 0. So I'll do this implicitly, all right? And so when we do that, based on the factorization, we see that x equals what? 1/2 is an x-intercept, and x equals -3 is an x-intercept. Now, so one note. When I mean, okay, xi is my shorthand notation for x-intercept. Okay, so let me write that down. And another thing to note is I kind of use the term x-intercept rather loosely. So in order to allay any confusion, let's make an x-intercept a point in the xy plane. All right, so if we're going to make an x-intercept a point, then by definition a point has what? An ordered pair, two pairs, right? So thus, technically speaking, the xi's, x-intercepts, are what? 1/2, 0, and what? -3, 0. So these will be our x-intercepts. So we have at least 2 points out of an infinite number of points that we can use to graph this figure. Okay, now, so we have x-intercepts, so now let's talk about y-intercepts. The y-intercepts, and I'll use y-i as the shorthand notation for y-intercepts, if any, okay, will be found by setting what? X equal to 0. So in this case, when we do so, the y-intercept, the yi for this function will be what? 0. So if x is 0, y is 3. I believe that would be the case if I plug in 0. Okay, so there's our y-intercept. So this is how we use factorization to get the x and y-intercepts. And now we have at least 3 points. We have 3 points that we can use to draw the graph. As I mentioned, there's another alternative, and that would be to use the another alternative to finding the roots of this quadratic, and that would be to use the quadratic formula. So let me do that on another page. So the next page. So let's go to Math, Equations, and the quadratic formula is this. So I'm going to put, well, hang on, I got ahead of myself there. So I'm going to write x 1, 2. Now the 1, 2 are subscripts. So subscript 1 means x sub 1. Subscript 2 means x sub 2, and the concatenation 1, 2 means that we are looking for what? Essentially 2 roots for this quadratic. And so x 1, 2 is equal to this formula. Okay, so this is the so-called quadratic formula. So let me rewrite the equation again for your reference. We have y is equal to -2x squared minus 5x plus, minus 2x squared minus 5x plus 3. So we can take the coefficients that are appearing in this quadratic, and we can wire them into the quadratic formula. And so when we do so, let's see what we get. So we have x 1, 2 is equal to, so let's replace, what do? We replace b with what? The -5, right? This thing will let me. So this would be -5. So replace all occurrences of b in this template with -5. And let me make this a little bit wider so you can see. And let's see, we replace a with what? We replace a with -2. Also, all occurrences of a with -2. And then we replace c with 3. All right, so we have this. And then we just solve. So when we solve, we'll get the same solutions, hopefully, as we got previously by factorization. So this would be what? Let me write this out. So we would have 5. Well, let me be more concise here. So we have x1 is equal to 5 plus the square root of what? 25. Now, on occasion, I'll make some numeric errors. You may spot those in my notes. I may not spot them. If you spot them, feel free to correct them and then send me a note, and I can inform the class of this. So I think sometimes I might write 24 and I'll say 25 and I'll write 24. That happens. Don't despair. Just let me know and we'll fix it. Okay. So this would be 25 plus what? 8 by 3 is 24, right? So we have 24. So this number is this sum is under the radical, divided by -4. So what happens when we simplify this? Well, this would be 5 plus, well, 25 and 24 are 49. Square root of 49 is 7. So 5 plus 7 over -4. And that is equal to -3. Is that what I got on the previous? I may not have gotten that. Let me check. Can we? Yes, we in fact did get -3 as a root. Okay, good. So far so good. Now we need to solve for x sub 2. Okay, so x sub 2. So x sub 2 is found by taking the negative of the radical, right? So that would be 5 minus the square root of 25 plus 24 divided by 4, -4 that is. And so that turns out to be -2 over -4. And I skipped a number of steps. So if you see me skipping steps like this, I have an expectation that you'll go back in and fill them in. Okay, so -2 over -4 is 1/2. All right, so there we have it. So we found the roots using 2 different techniques, which led to the intercepts. Now, what is it about parabolas that we're oftentimes interested in? And that is, we want to find the vertex of the parabola. So we want to find the vertex of the parabola. Okay, now in 107, I believe, or from your previous math experiences, you may have noticed that there was a formula, a particular formula for calculating the vertex. Well, I've seen it, I've taught it, but unfortunately I can't remember it. So, and I pretty much suspect that many of you don't know it either. And so we need a technique for calculating the vertex of a parabola. And so one of the more convenient ways, a way that doesn't involve having to memorize it, would be to use a technique called completing the square. All right, so what would that entail to complete the square of the parabola? Well, to complete the square, okay, so let me write this down. Use completing the square technique. All right, so the first thing you want to do is look at your parabola right here, your equation. So let's see if I can. Here's our equation right here. So let me bring this down. So here's our equation. Now, first thing we'll do is step 1. Factor the leading coefficient. Let's do it. This is going to take too much time. Let me type this. Let me just go ahead and type it. I can type faster. Okay, so factor, step 1. Factor the leading coefficient from the first 2 terms. All right, so first of all, what is the leading coefficient? Well, the leading coefficient is, as you probably can guess, is this number right here. It's the coefficient on the term with the highest exponent right there. So in this case, what we want to do is we want to factor -2 from the first two terms right here. So when we do that, we get y is equal to -2 times x squared plus 5/2. Okay? Plus 3. So what I did is I factored -2 from the first two terms. Now, how do we know? Oh, that should be 5/2 x, sorry. 5/2 x. Okay, so how do I know this factorization is correct? Well, another concept that I expect you to be familiar with in this class is the idea of distributive property with respect to addition. So if we take the -2 and we distribute it term by term to the terms in parentheses, we'll have -2x squared, -2 times 5/2 is -5. So we'll have a -5x plus 3. And so we can get back the original equation. So that's the first thing we need to do when we're completing the square. Okay? Factor the leading coefficient. All right, so now what's next? Second, step 2, take 1/2. Take 1/2, should be 1/2. Hello, 1/2. 1/2 of the coefficient on x. So in this case, the coefficient on x is 5/2. So according to step 2, what we'll do is we will say take 1/2, and so we get 5/4. All right, just do that. All right. Okay, so the next thing we do is with that 5/4, step 3, square the number from step 2. Okay, so just square 5/4. So what happens when we square 5/4? Well, let's see here. Let's do that. So we will get, what, 25/16, right? All right, so that's from step 3. Okay, moving right along. Step 4. Add the number found in step 3 to the terms in parentheses. Okay, all right, so let's do that. So if I were to do that, here's what we would get. So we would have y is equal to -2 times x squared plus 5/2 x plus 25/16. Okay, so we've added it to the terms in parentheses like that, plus 3. Now, the issue that has arisen now is that when we add this 25/16, we no longer have the original equation, right? These two equations are no longer the same. Not the same, okay? So our adjustment in hunting for the completion of the square, it's not the same. So how do we make them the same? Well, it turns out to make them the same, we need to make an observation here. We note that what we have effectively added to the parabola, to the original parabola, is this number right here. Right here. -2 times 25/16, right? So we have added -50/16 to our parabola. Okay. So in math, when you add a number such as this, -50/16 to the parabola, to retain the original equation, you have to subtract off the same number that you've added. Okay. So I'm hoping that you recognize that in completing the square, we've added -50/16, and now we have to subtract -50/16. And so now these two equations represent the same thing. All right, good. So what next? So now that we've made these adjustments, so this is I kind of combined a lot of steps into step 4. So, but I think you get the point. So now step 5 would be step 5. Express the trinomial in parentheses as a binomial square. Okay, so in other words, you have to take this trinomial and express it as a square. And it turns out if you did the completion of the square properly, then this would be a perfect square. So this trinomial, if done correctly, should be a perfect square. So when we do that, we get y is equal to -2 times what? X plus 5/4 quantity squared. And what I'm going to do next, also, while I'm at it, I'm going to go ahead and simplify this difference right here. So 3, of course, is 48 over 16. 3 plus 50 over 16 would be what? 98 over 16. So we have 98 over 16. Okay, so here's our quadratic expressed in a vertex, in a form where we can extract the vertex. I think, what is it, standard form or something like that? I believe, I can't remember the terms. It's not relevant at this level. But once we have this information, we can pick off the vertex, because the generalized representation of a parabola is something like this: a times x minus h squared plus k. All right. So whenever you see a quadratic formula written in this format, the vertex turns out is hk. All right. So that's why we use completing the square, so that we can extract the vertex. So in this case, in our case, our vertex would be, well, in this case, h is -5/4. So -5/4. And our k value would be, well, let's go ahead and reduce it. That would be 49/8. Okay, reducing the fraction. So there's our vertex. So now we have 4 points we can use to graph this function. All right, so next page. All right. So let me copy that formula again so we can reference it. Copy, next page. There we go. Okay, so here's our formula for your reference. Okay, so another thing to consider is, now as we draw this parabola, there's some additional information that's useful in this equation, and that is the leading coefficient. That leading coefficient tells us the direction in which the parabola is going to be pointing. Now, since this is a function of x, we have a choice of the parabola going in this direction or the choice of the parabola going in this direction. And the direction of the orientation, whether it points up or whether it points down, depends on the sign of the leading coefficient. So since leading coefficient is less than 0, okay, we will have parabola will point down. Let me go ahead and type this. It's easier to type. So let me summarize better. Okay, since the leading coefficient, is less than 0, so the parabola will point down. If the leading coefficient were greater than 0, then the parabola would point up. All right. So another consideration to make is what this means in terms of the vertex. All right. So if the parabola, that is, points up, then the vertex is called an absolute minimum. Otherwise, okay, so if the parabola points down, then the vertex is called an absolute maximum. All right, so in this case, the vertex that we calculated on the previous page will be an absolute maximum. That means that no other point on the parabola will be above this point. This point is the peak of the parabola. All right, so do we have any other things that we need to know? Oh, yes, one other note. The vertex happened at which point? -3, what was it? It was, oh, I'm sorry, it was -5/4, -5/4, 49/8. All right. Okay. The axis of symmetry is another the axis of symmetry is x equals -5/4. And this is kind of a vertical line where both branches of the parabola, one branch of the parabola is reflected about this vertical line, and we'll see it as we draw the graph. So we have enough information to draw the picture of this parabola, so let's give it a go. Let's try and, so we want to start, say, from -5 to 5. Okay, so let's see if we can draw the parabola on this grid. So what do we have? We had two x-intercepts, which occurred where at 1/2 and 0. What color do we want to use? Oh, let's try green. So we have, there's an intercept, and the other one was at -3, 0. And then we had a y-intercept at, where was our y-intercept at? 0, 3, right? So there's our y-intercept. That looks kind of strange. Did I get that right? Let me check. Let me check my intercepts. Let me check. Oh, it was 1/2 and -3, yeah. And then, okay, yeah. And then we had a vertex at -1.25 and 6.125. So -1.25, so 1 1/4, and 6 1/8. So there's our vertex. And knowing the leading coefficient is negative, we know that this thing points down. So very carefully sketch. I'll try to connect the dots as best I can. That's not very nice. It's not a very good sketch, is it? So let me try it again. All right, try it again, Russ. Okay, so 1/2, 3, -1.25, and 6 1/8. Okay, so you have to kind of be free-flowing, freestyle, right? Sorry. I'll get it right. Trying to draw with the mouse isn't the easiest thing. All right, so let me try going at it from this angle. Still not right. Let's see, I need my pen tool. And green, okay, so 3. Let's see, let me do it piecemeal. Okay, so this is one branch, and then the other branch will go like this. Okay, without the flares there. Okay, so now there's our graph of our parabola, and then we have our axis of symmetry, which I'll draw in blue here. And note that, so the axis of symmetry should be x equals, I think that's negative 1.25. And I'll call AOS the axis of symmetry. And note that the parabola is symmetric with respect to the axis of symmetry. So let's see how it would look in a different context. So on the class website, I've got a graphing calculator that you can use to explore graphs with. So let me see if I can pull that up using a web browser. So let me insert a browser, okay, and let's go to the class website. So let me type that in the browser bar. Hopefully it'll go there. Okay, there it is. And so here's our trigonometry class website, and then we have this graphing calculator. And so our numerator is basically the polynomial itself, so that would be minus 2x squared minus 5x plus 3, and our denominator is simply 1. And we can just stick with the x min, x max, y min, y max. That's basically your zoom box. Submit, and let's see what the drawing looks like. Computing, right? There's the plot, and there's our graph, which looks very similar to the graph we just constructed. So, yeah, here it is. So here's our parabola. Right there. How nice that looks. Okay, so there you have it. All right, so moving on. So the next topic I want to review for would be equations of lines. Just a quick review. There are two generalized formats for lines, which we'll go over. So let's do this on the next page. All right, so the first question regarding lines we ask is this. What is the equation of the line connecting the point x1, y sub 1 with the point x sub 2, y sub 2? Now, there are a couple of ways we can go about doing this, okay? We can use the so-called point slope formula. So what is the point slope formula? Let's see if there's one in algebra. No, there's not one in algebra. Of the one in statistics, maybe. I don't see one there. Maybe in trig. Not in trig. Geometry. Okay, so I'll have to handcraft it. Okay, so using the point slope formula, we have y minus y sub 1 is equal to, oops, that should be 1, right? Oh, strange. Is equal to m times x minus x sub 1. Okay, so this would be the so-called, this is the point slope form for the equation of a line. This is the point slope form for the equation of a line. Now, in this case, I chose to build my equation using y1 x1. I could have easily chosen to build my equation using y2 x2. So let's see. In other words, I could have done this. Let's see if I can copy this. Control C, Control V. So another technique could have been Oops, I don't think that's going to work. I'll just go ahead and use the math equation editor again. I could have said y minus y sub 2 is equal to m times x minus x sub 2 as well. So both of these, depending on your choice, either of these would yield the same result. Okay, so there you have the point slope form. So let me give you an example. So let's say I give you x, let me define the point x sub 1, y sub 1 is equal to say 5 halves, negative 5 halves, and 3. So let's make this negative 5 halves and 3. All right? And let's define our second point as x sub 2, y sub 2 is equal to, what do I have? I have 1/2, 0. Okay, and so the objective here is to find the equation of the line connecting these 2 points. So using the point slope form, we have to calculate the slope, right? So slope, we'll use the first form. We'll use equation number 1. We could use either equation, but we'll use number 1. So slope is equal to what? y1 minus y2. So that would be 3 minus 0 divided by x1 minus x2. So that would be minus 5 halves minus 1/2. So we first calculate our slope, and that's equal to 3 divided by negative 3, which is equal to negative 1. Now that's one way of calculating the slope. I could have also said that m could equal to y2 minus y1 over x2 minus x1. This is an alternate formula for the slope. So either way, I should get negative 1. So you work it this way, and you should get negative 1 as well. So now, like I said earlier, I'm going to use equation number 1 to calculate the equation of the line. So doing that, I'll have y, and what is y sub 1? Y sub 1 is 3, right? Here's my y sub 1, is equal to slope, which is negative 1, times x minus x sub 1, which is negative 5 halves. And we'll simplify this. All right, so that we're left with y minus 3 is equal to negative x minus 5 halves. So check the algebra there. So let's bring the negative 3 over. So we have y is equal to negative x plus 1/2 after simplifying. Okay, so as you can see, I skipped a number of algebraic steps, but I expect you, if you don't see this readily, I have an expectation that you can go back in and fill the details since this is an algebra review. Okay, so there's our equation. What else? Okay, so that's the point slope format. The other format that we're going to be dealing with is the slope intercept form. So let's talk about that. In slope intercept form, all right, so the other format for the equation of a straight line is the slope intercept form. All right, so slope-intercept form. That is typically written like this. Y is equal to mx plus b. All right? So what is b? So b is the ordinate of the y-intercept. Now, a little bit of terminology for you. When I give you the coordinates of a point, x is called the abscissa, and y is called the ordinate. All right, so two terminologies, the components of the xy pairs of a point, of the definition of a point. So with this in mind, b is the ordinate. The y-intercept, spell it right, is what? 0b. Now I know it's the literature and the homework problems kind of get mixed up at times. They say, what is the y-intercept of an equation? And you just write b down. Well, technically speaking, y-intercept is a point. So let's make this clear. Note, y-intercept is a point, not a number. Okay, so when I ask you, what is the y-intercept, I expect you to write it as a coordinate pair, 0, comma, some number, right? So not a number, just don't write a number. If you write a number, you're technically not correct, okay? Y-intercepts are points. Okay, so with this in mind, we can use the y-intercept form to calculate the equation of a line. And it turns out that if we look at the equation, it's already in y-intercept form, right? In this case, our y-intercept, in the example that is, the y-intercept is equal to 0, 1/2. Although we used point slope to calculate the equation of the line, when we finished simplifying it, it turned out to be in the same format as the y-intercept. So we got lucky with that one. Okay. All right, what next? Okay, so the next thing we want to talk about is the distance between 2 points. All right, so I'll do that on the next page. Distance between 2 points. Oops, I should write carefully. A and B. Okay, so we have 2 points. A is equal to x1 sub 1, y sub 1. B is equal to x sub 2, y sub 2. And we want to calculate the distance between those two. And of course, the technique is we use the so-called distance formula. So what is the distance formula? Well, it stems from the Pythagorean theorem, and many of you probably don't remember, so I'll illustrate it here. So the formula goes like this. Close is equal to the square root of x 1 minus x minus x 2 squared plus y 1 minus y 2. So here's our distance formula. It's the square root of the distances between the abscissas plus the square of the distance between the ordinates. Okay? So this is the formula we'll use. So for instance, if we go back and say we want to find if we let A, let's let A equal to, negative 5/2 3. And we let B equal to negative 1/2, or how about a half? Let's make it a half. 1/2, 0. All right, so what we're pursuing here is we want to find the distance between A and B. So D AB is equal to, let me see if I can copy this. Control C, Control V. So DAB, is there an edit mode? Let me check. Math, equations. Not sure how we can, I don't think it's going to let me edit. Yeah, here we go. Double click. Double click puts you in edit mode. So x of 1 in this case would be negative 5/2. So what we do is we type negative 5/2, and then x of 2 would be what? A half. All right, and then y sub 1 is 3, and y sub 2 is 0. All right, so then we simplify this expression, and so that would equal to the square root of, well, negative 5/2 minus 1/2 is what? Negative 3, so we'll have negative 3 quantity squared plus 3 squared, right? Which is equal to the square root of 18, which is equal to 3 on the square root of 2. So that would be the distance between those 2 points. Another topic we were interested in is finding the midpoint of the line segment connecting the 2 points. So find the midpoint of the line segment connecting the 2 points. So we need the so-called midpoint formula. So the midpoint formula goes like this. That would equal to let's see, that would be x sub 1 plus x sub 2 divided by 2. And then the ordinate would be, well, this is the abscissa. So this formula right here that I've got highlighted, that's the abscissa of the midpoint. And then the ordinate would be this, the average of the y values, right? So that would be 1, y sub 1, plus y sub 2 divided by 2. So there's the formula, the general formula for the midpoint of the line segment connecting the 2 points. So if we have A and B, and say we plot them in the XY plane. So let's see if I can do that math, the graph. Wizard. Next. So let's start at -2, -3, -4. Go to 4. And then y will just make a square grid, -4 to 4. All right, so let's find the midpoint of A and B. So A got truncated, didn't it? Can I copy this down? Extend page. Change the cursor. Let's see if we can, yeah, I think I can move this around. Yeah, okay, so here we go. So here's our, oops, I covered up the formula, didn't I? All right. So A is negative 5/2 3. So let's plot negative 5/2 3. So that would be, oh, negative 5/2 3 is here. So this is our point A. And B is what? 1/2 0. So B is 1/2 0. So there's B. And so we want to find the midpoint of this line segment. Oops, sorry. My hand slipped. My hand slipped when I was drawing it. Try it again. So there's my A. All right, so let's draw it. Okay. So there's my kind of curvy line segment. Okay, so all right. So what is the midpoint? So in this case, our midpoint would be the coordinates of our midpoint would equal to negative 5/2 plus 1/2, which is negative 4/2 over 2. So we'll have negative 5/2 plus 1/2. All of that divided by 2. That's the abscissa. The ordinate would be 3 plus 0 divided by 2. 3 plus 0 divided by 2. And so when we simplify that, that's equal to, well, the numerator for the abscissa is negative 4/2, negative 2. Negative 2 divided by 2 is negative 1. And 1.5 would be the ordinate of the midpoint. So we can plot that. Negative 1, 1 point. Oops, where did my cursor go? So there's our midpoint right there. Okay, so that's it in a nutshell, the midpoint. All right, not too bad, right? All right, so extend the page. And let's talk about a miscellany of other things we can deal with. We can, of course, talk about what is the equation of a line parallel, or we can talk about parallel lines. So note, lines that are parallel have what? Have the same slopes. Okay? The slopes of lines which are perpendicular are negative reciprocals. Okay, so for instance, we had an equation back on one of the slides, right? What was it? Let's take this one. Y is equal to negative x plus 1/2. So let's go to the next page. Let's go back to the page. And let's say, extend page. So let's say, okay, so let's write this. So we have y is equal to negative x. Let's change it up a little bit. Let's say negative 1/2. Negative 1/2 plus x minus 3. All right, so we have this equation of a straight line. So say we want to find the equation, of line perpendicular to y with y-intercept, say 0, pi. To make that clearer. Okay, now a symbol for perpendicularity, which I'll be using a lot, would be this upside down T symbol. So please note that this is a symbol for perpendicularity. All right, so now to solve this, to answer this question, we note that perpendicular lines have, the slopes of perpendicular lines are negative reciprocal. So the negative of the reciprocal of negative 1/2. Well, what is the reciprocal of negative 1/2? So the reciprocal of negative 1/2 is negative 2. And then we negate it. So m is equal to 2. So the slope of a line perpendicular to this line will have a slope of 2. The product of the slopes must be negative 1. And it has to have a y-intercept of 0 pi. So therefore, our equation, which I'll call this, see this y with a v on top, this is read y hat. Okay, so y hat is equal to mx, 2x, plus the ordinate of the y-intercept. So it would be y is equal to 2x plus pi. So here we have it. We have this line is perpendicular to, these two lines are perpendicular. And this line right here has a y-intercept of 0 pi. Okay, so that works out that way. All right, so that's all I want to say at this level about equations of straight lines. We're going to use this quite extensively. If you have any questions, please feel free to contact me or visit with a tutor or look at some online notes if you want to have some more advanced problems in this area. As we encounter more advanced problems in this area, I'll try to introduce the necessary material as we go along. So the next topic I want to talk about with regard to functions would be the notions of increasing and decreasing functions. So the notions of increasing and decreasing functions. A function f is increasing on an interval x1 to x2. Okay, this is a closed interval. If f of x2 is greater than f of x1 for all x1, x2 on the closed interval. Okay, so in other words, it looks something like this. An increasing function will have this kind of look to it. So here's my xy axis. So here's x, here's y, and an increasing function will go like this. So as you see, as x increases, y correspondingly increases on, say, this particular interval. Right, so here's my x1, and here's my x2. So note that as x increases here, y increases on that interval. It never, in other words, you never see anything like this, what I'm showing in red, happen. You never see anything like this, okay? Here in this case, as x increases, there's a, in this red zone, you'll see that y decreases for some values of x, right? No, this will not happen. As x increases, y correspondingly increases. So with that in mind, we also have the notion of a decreasing function. Likewise, f is decreasing on an interval x1, x2, on the closed interval x1, x2, if fx2 is less than fx1 for all x1, x2 on the closed interval x1, x2. Now, I'm going to loosen this up a little bit. I'm going to say, instead of strictly greater than, I'm going to say greater than or equal to, or less than or equal to, right? So we'll call these, we'll use these as the framework for increasing and decreasing functions. The reason why I mention it at this point is because when we start graphing trigonometric functions, we'll need to know this kind of information. And let me sketch you sketch for you an example of a decreasing function. So here's my xy plane. Okay, and here would be an example of a decreasing function. So note that, okay, so we can make this x1, and we can make this x2. So as x increases, note that each succeeding value of y, or y correspondingly decreases as x increases. So this would be a decreasing function. Some symbology that we use, we say that y is decreasing here, and we say that y is increasing here. So when you see the up arrow, that means it's increasing on an interval. All right, so those are kind of loose definitions for increasing and decreasing functions. All right, so the next topic we're going to be dealing with would be graphing rational functions. And I've got a couple of examples I'll show you. Just checking to see how far we have to go. Okay, so we're making good time. Graphing rational functions. So I'm going to give you 6 steps on how to graph a rational function. Each step will have multi-parts, of course. So the first thing we want to do when graphing rational functions is we want to check for symmetry. Check for symmetry. So recall that our rational function f of x is equal to p of x divided by q of x. So in checking for symmetry, we want to check for even symmetry. So even symmetry means that the graph, so if f of x has even symmetry, then it is symmetric with respect to the y-axis. And this occurs when f of minus x is equal to f of x. All right. So if a graph has this property, then it has even symmetry. I'll give you an example of this in just a second. The other type of symmetry we need to investigate would be odd symmetry. So take this down for now, and we'll go over some examples. So if f of x has odd symmetry, then it is symmetric with respect to the origin. This occurs when f of minus x is equal to f of x. All right, so can you think of us some examples or an example of a function that possesses even symmetry? Well, the classic example would be what? Y is equal to x squared. So consider the fundamental parabola. So let me just go ahead and sketch it. No, I guess I could go ahead and use the insert internet browser. Okay, so let's do that. Oh, I need to go in cursor mode, don't I? All right, so let's go back to our graphing calculator. So the numerator, we're going to graph y equals x squared. Now, one note about using this graphing calculator. Always put your numerator and denominator in parentheses. For some reason, it's an idiosyncrasy of this calculator. Okay, so if we submit, and so what I'm trying to show you is the property of even symmetry of a graph. And here it is. What even symmetry means is, you see this graph of y equals x squared? Y is equal to x squared. What it entails is, if we select a point right here, suppose we pick any arbitrary point other than the origin on this graph. So xy. If xy is on this graph, then it has a symmetric counterpart, negative xy, owing to the symmetry with respect to the y-axis. Okay, so this is a property of graphs with even symmetry. The utility of even symmetry when drawing graphs is if you can calculate this point. If you go through some rather complex calculations to get the coordinates of this point, then you don't have to calculate the coordinates of this point. You automatically know that you just negate the abscissa, reuse the ordinate, and this point is plotted. So half the work is already done. So there is a tremendous advantage in knowing whether a function is even or not when it comes to graphing. Okay, so let's see here. Dismiss this graphing tool for now. We'll come back to it. Okay, so that's an example of even symmetry. Can we do an example of odd symmetry? Well, the classic example of odd symmetry would be, can you think of a function? Say y equals x cubed, right, from your algebra class? All right, so y is equal to x cubed. So let's see what that's all about. Y is equal to x cubed. We want to show that it has odd symmetry. But before I proceed, I see a mistake I made in my notes. Let me just make one correction. Odd symmetry happens when f of negative x is equal to negative f of x. So before we validate using graphical techniques that y equals x cubed has odd symmetry, let's just go ahead and work through this particular formula. All right, so what is f of negative x for this function? Well, this would be, let's go back to my pen tool. So let's write it this way. F of x is equal to x cubed. We want to demonstrate that this function has odd symmetry. So to do so, we calculate f of minus x. Now, what is f of minus x? Well, that means wherever we have an x, we replace the x in the formula with minus x. So we substitute minus x for x in the formula and cube it. And so negative x quantity cubed is simply negative x cubed, which is equal to minus f of x. So that demonstrates that y equals x cubed has odd symmetry. Okay, and we can go ahead and validate this graphically. So let me insert the browser back in. And let me put the, go back here. Let me put the URL back in. Go down to the graphing calculator. And so the numerator is what? X, let's see, x cubed, right? Okay, and the denominator, of course, is just 1. We can just put 1 right there. Submit, and we should get our graph of y equals, I guess I have to put 1 in parentheses. Okay. Oh, it showed up. Okay, it's just a bit on the slow side. All right, so here's the classical graph y equals x cubed. Now, to demonstrate what symmetry about the origin means, all right, so let's just go ahead and put a dot at the origin. So there's a dot. Now, a graph that has symmetry with respect to the origin, if we pick any point right here, say xy, any arbitrary point, if this point is on a graph with odd symmetry, then its symmetric counterpart would be the negative of the abscissa. Oops, sorry, that's kind of not worded very well. Let me try again. The symmetric counterpart would be the negative of the abscissa and the negative of the ordinate. So there's your symmetric counterpart. So again, there's a utility here. If you go through a lot of work to calculate the coordinates of a point, on a graph with odd symmetry, then you can plot an additional point without further calculations by just negating the abscissa and the ordinate and explaining the fact that it has odd symmetry. So if this is on the graph, then this point is on the graph. And if it doesn't happen that way, then you probably have a mistake somewhere and you need to go back and recheck your work. All right, so examples of odd symmetry. Comes in very handy when you're working with graphs of rational functions. All right, so that's all I want to say about symmetry. You can see that it can really almost have the amount of calculations you have to do if you do it right. And so let's go back to checkpoint number 2. All right, so number 2, what do we do next? All right, so the next thing we want to do is we want to find the vertical asymptotes of the rational function. Find the vertical asymptotes. All right, so the way the procedure is, if there are no common factors, of P of x and Q of x for y is equal to P of x divided by, y is equal to, P of x divided by Q of x, then the real roots of Q of x, if any, determine the vertical asymptotes. Which I'll abbreviate as VA. VA stands for vertical asymptotes. Okay, now, what happens if there are common factors? All right, if there are common factors, in other words, you can cancel a common prime factor out of the numerator to denominator, well then the root of that common factor becomes a whole. And I think I have an example of dealing with those, maybe not. Not quite. Well, let's say, let me give you an example of what would be a whole while we're at this. I'll take a brief diversion here for a second and show you if there is a common factor in P of x and Q of x. So let me insert the web internet browser again and go back to the website. Show you how to deal with a whole. It's a topic that, interestingly enough, is not covered too much in the algebra sequences, but I'll cover it here. All right, so we'll go here, and let's go back. Let's go down for the graphing tool. There it is. Okay. So let's consider this. Oops, sorry. That's not what I wanted to say. Let me write it. So let's consider this rational function, the graph. Again, I'm trying to show you how to determine a whole. So if we have, say, f of x is equal to x plus 1 divided by x squared minus 1. Okay, this graph will have only one vertical asymptote, and that would be at x equals 1. It will have a whole at x equals -1. All right? So here's why. When we factor the denominator, okay, as you can see, the denominator is a difference of 2 squares. So from your factoring knowledge, it's going to look like this. All right, so there's our expression for our rational function. And you can see that the x plus 1s will cancel. All right, so the x plus 1s cancel like that. When you have a cancellation of a prime factor in the numerator and the denominator, what happens is that you will have a whole hole at x equals -1. And the coordinates of the hole will be -1, 1 over -1 minus 1. Okay, this will be the coordinates. All I did is after I did the cancellation, I just took the -1 and I plugged it in there. And so we'll have an open circle at -1, -1/2. And then we'll have a vertical asymptote at x equals 1, because the graph clearly cannot exist at x equals 1. All right, I'm not sure if this graphing calculator will show the presence of holes, so let's dwell into it and see if there's a limitation. Oops, I lost track of it. Browser's cached. Okay, let me go back to it. Sorry if that went too fast for you. The recording exists, and you can, and I'll print out the lecture notes so you can capture it in a slower mode. This may have, I accidentally hit the backspace key, and I lost the equations I had shown. But anyway, I'll show you. We'll go ahead and graph it. Put back on arrow mode. Okay, go back here. Put here. So it was what? X plus 1. Okay, that would be our numerator, and then our denominator is x squared minus 1. Okay, and then let's make x min, x max. Say we'll go change our zoom box boundary from -5 to 5, and we'll just leave y min max the same. Okay, and let's see what happens when we graph this. So we are expecting a vertical asymptote at x equals 1, which we do. Here's our vertical asymptote right here. But at the same time, what's not shown would be a hole at, what did we say it was? It was at -1/2. No, -1, excuse me, -1, -1/2. So we should have a hole right about there, okay? This graphing utility doesn't show it very well. Maybe if I zoomed in, let's see, let's explore further. Say between -2 and -0.5, and let's say -3 and 0. Let's try this. Let's confine our zoom box there, and let's see if we can see if this thing actually does depict a hole. There's our graph. Did it not do the graph? Evidently not. Okay, well, we can explore that at another time. Yeah, these Wolfram widgets aren't the greatest of graphing applications to use. So, okay, so I'll leave that to you to explore further. So where were we? Okay. All right. Oh yeah. So here are our equations. So let me delete this, and let me erase all of this scribble stuff here. So nevertheless, you saw the example of a vertical asymptote after you canceled all of the common factors. All right. So what's next? Okay. The next thing we want to do is we want to calculate the x and y intercepts. All right. So we can make a go at that. All right. So in step 3 of 6, okay, find the x and y intercepts. Okay, so to do so, P of 0, of course, is the y-coordinate, is the ordinate of the y-intercept for f of x. Easy enough, right? Right. So set P of x equal to 0 and solve to find the x-intercepts, assuming that once you solve it, that it is in the domain of the function. So make sure that your values of x are in the domain of f of x. Okay. All right. So x-intercepts. Okay. Step 4, find the horizontal asymptotes. If any. All right. So before we find the horizontal asymptotes, I need to give you a definition. The degree of f of x is equal to this formula and is the largest exponent in the function. All right, so we need to know what a degree of a polynomial is so that we can calculate the horizontal asymptote. So using this knowledge, if the degree of P of x is less than the degree of the denominator, degree of Q of x, remember Q of x is the denominator, then y equals 0 is a horizontal asymptote. Okay. Likewise, if the degree of P of x is equal to the degree of Q of x, and the degree of P of x is equal to P, and the degree of Q of x is equal to Q, then y equals to P over Q is a horizontal asymptote. Okay, so you have to be on the lookout for that. And of course, if the degree of P of x is greater than the degree of Q of x, then you have to divide the two, and essentially there won't be a horizontal asymptote at this juncture. More on that later, though. All right, so horizontal asymptotes, and I'll give you an example in just a few more, after just a few more notes. All right, so we have vertical asymptotes, we have horizontal asymptotes, and then the other category of slant asymptotes would be the slant asymptotes, okay? So we want to find slant asymptotes, if any. And I'll abbreviate slant asymptotes as SA, all right? So to find a slant asymptote, if the degree of P of x is equal to the degree of Q of x plus 1, then f of x will have a slant asymptote. Okay? So divide P of x by Q of x and discard the remainder. All right. So I will show you that in just with the next example. All right. Step 6, the final step, would be to determine the intervals on the x-axis where P of x, I'm sorry, not P of x, f of x is above the x-axis, and f of x is below the x-axis. And I'll show you the technique for doing that as well right now, as a matter of fact. So, next slide. So make sure you get all these steps down. We'll use them often. So, for example, let's consider the function. We want to graph this function. F of x is equal to x squared plus x minus 2 divided by x minus 3. So that's our objective. We want to graph this function using the techniques we just described. So the first thing we want to do is we want to check for symmetry. All right. So check for even symmetry. What is f of minus x? So in our check for even symmetry, that would equal to minus x quantity squared minus x minus 2 divided by minus x minus 3. And that clearly does not equal to f of x. So this function has no even symmetry. It's not symmetric with respect to the y-axis. Also, looking at this expression, it does not equal to negative f of x. So this graph is not symmetric with respect to the origin. So therefore, this graph has no symmetry. All right, so no help there. Next, we want to find the vertical asymptotes. Well, we can almost do that by inspection. If we factor the numerator, and the reason why we want to factor the numerator is to check to see if we have any holes or any cancellations. The numerator factorization would be x plus 2 times x minus 1, right? Oops, sorry about that. Try again. X plus 2 times x minus 1 divided by x minus 3. All right, so there are no cancellations in the numerator and the denominator. So it follows that the vertical asymptote is x equals 3. Okay. What next? X and y intercepts, right? So the x-intercepts are found by setting p of x equal to 0. So p of x equals to 0. And that's almost trivial. We can just use the factorization from step 2, and so we see that we have 2 x-intercepts. One at negative 2, 0, and the other at 1, 0. Okay. And note that negative 2 is in the domain of the function, and 1 is in the domain of the function, so there's no issue there. The y-intercepts are found by setting x equal to 0 in f of x, so f of let's see, the y-intercepts, what was the rule? P of 0, right? So if we set p of 0 is equal to what? If we plug in 0 here, that would be negative 2. So the y-intercept would be 0, negative 2. Is that right? Yeah. So, all right. So we have at least 3 points on our graph now, right? Okay. Next, we want to analyze to see if there are horizontal asymptotes. Well, the degree of p of x is 2. And the degree of q of x is 1. So, based on our rule for extracting horizontal asymptotes, this function has none. So there are no horizontal asymptotes. Right? But if we note that the degree of the numerator is 1 more than the degree of the denominator, we do have a slant asymptote. All right, so yes to slant asymptote. And so we have to calculate that. Because p of the degree of p of x is equal to degree of q of x plus 1. That should be a plus 1 there. Okay. All right, so on the next page we'll calculate it. Now to calculate the slant asymptote, the rule is that we divide the denominator into the numerator. And my technique of choice would be to use long division. And I understand that some of you probably aren't familiar with long division of polynomials. You can try synthetic division if you're more familiar with that. That will work just as well. But I'm not going to spend any class time reviewing on how to divide two polynomials. That should have been covered in the algebra sequence. If you struggle with this, please seek some quick remediation on this concept. It's not that difficult, and patch that in as soon as possible. If you still have difficulties with it, come see me and we'll talk about it. But let me see if I have another assist for you when it comes to long division or division of polynomials in general. I thought I had a long division polynomial calculator. Let's check. Possibly, possibly not. I can't remember. I'll check the website. Checking. Slow. Internet's slow this time of day. Everybody's getting home from work and hitting the internet. Okay, so let's see what kind of calculators we have. Polar graphing and conic section. Oh, okay, yes, we do. Yeah, so if you go to the class website, here we have a polynomial division calculator. So in this case, if we take x squared plus x plus 2, which is our numerator, that's our p of x, right? And again, I'm putting the quantities in parentheses, and we divide by x minus 3, which is our denominator, and let's see what the result is. Well, if it will give us a result. I'm not seeing it. Maybe there's an error. Oh, I have to scroll over? Okay. Oh yeah, so here we go. So here it is. Here's the division, the result of the division right here. And you'll see that this 14 quantity right here, that is your remainder. Okay? And this quantity right here, this is your quotient. So this would be your slant asymptote. All right? So your slant asymptote is y is equal to x plus 4. Now I'll show you how you can get this result using long division of polynomials. Note that we discard the remainder. All right. So let me demonstrate this for you. Okay, so what we want to do is we want to conduct a long division. So we will divide x minus 3 into the numerator. Oops, I need more space. Let me erase this. Need more space. X minus 3 into the numerator, which is x squared plus x minus 2. Now, long division of polynomials is the same as long division of numbers. You look at your divisor, which is x minus 3, and you inspect and see, ask yourself, how many times will x minus 3 go into the first two terms of the, I guess this is the dividend. And you say, well, okay, let's try x. Okay, so x times x minus 3, you multiply this, okay, that would be x squared minus 3x. And then you do the same thing as you would do with numbers. You subtract the two quantities. So x minus 3x is 4x. And then you bring down the remainder. Okay, and then you ask yourself again, how many times will x minus 3 go into 4x minus 2? Just like you do with numbers. And you say, okay, it'll go 4 times. Okay, so 4 times x minus 3 is 4x minus 12. And then you do the subtraction and you have minus 14. So this is your remainder. Discard the remainder and retain the quotient, which is right here. So this would be your slant asymptote. So our slant asymptote is y is equal to x plus 4. So it's a line. Now later on in this class, we're going to have different kinds of slant asymptotes. There'll be different kinds of functions. So expect that later on in the class, and I'll show you how as we get more advanced. Okay, so what else is there to show? We've got intercepts. Oh, I believe we stepped through all 6 of the items. Okay. Oh, no, I'm sorry. We have to do the where the graph is above and below the x-axis. Okay, so I'll do that on the next page. All right. Sorry about that. Step 6, I forgot. Okay, so let's rewrite our function again. So f of x is equal to, oh, let me pull it back. What was it? It was x squared plus x minus 2. So that was, what I'll do is I'll go ahead and factor it. Factor the numerator and denominator. So in doing step 6, you have to factor completely the numerator and the denominator. That's the first thing you want to do, factor. All right? Okay, then the next thing you want to do is you want to build a table. So let's see if I can insert a table. Okay, so the number of columns will be 4, and the number of rows will be 4. The number of columns will be 5. Okay. All right, so here we have this table, and I'll show you what content to put in this table. In the first column of the table, we're going to put each of the prime factors. Each of the prime factors that appear in f of x. So what we'll do is we'll put x plus 2 here, and x minus 1 here, and x minus 3 here. So you see in each of these cells, I'll put the prime factors. Now, if it turns out that one of these prime factors is repeated in f of x, then you'll repeat it here in this first column as well. Now, in the last cell of the first column, I'm going to write f of x. Like this. Okay. So there's the content of our, this is called the table of signs. Okay. For lack of better terminology. and it's used to help us identify where the graph is above and below the x-axis. So table of signs. Okay, just for future reference. All right, so when we construct this, the next thing we want to do is we want to identify the x-axis. Okay, so the x-axis is this line right here. We'll call this the x-axis. It separates f of x from the factors above. So call this the x-axis. And we'll call this minus infinity, and then we'll call this plus infinity. Okay, so there's the entire x-axis. So that's the next thing we want to do. So draw your x-axis on the line above f of x. All right, the next thing we want to do is we want to identify the zeros of each of the prime factors. Okay, so the 0 of x plus 2 is minus 2, and then we'll plot it on the x-axis. Now, since negative 2 is in the domain of the function, what we want to do is we want to put a solid line. We want to fill this in with a solid line like this. Okay? And another 0 of a prime factor is 1, so plot 1 on the x-axis. And since 1 is in the domain, make that a solid line like that as a separator of columns. Okay, like that. And then the other 0 is 3, so plot 3. So you see we plotted all the zeros of the prime factors. But 3 is not in the domain, so instead of a solid line, make it a dashed line, as in a dashed line for a vertical asymptote, right? So this is one of the techniques that I often use. Okay, so now we need to fill in these 12 cells with information. All right, so what goes in this? Well, what goes in this is the answer to a question. And the question is, if I choose any number between negative infinity and negative 2, and I plug it in to this factor right here, what would be the sign of that factor? So for instance, negative 4 is between negative infinity and negative 2. So if I take negative 4 and I plug it in for x, negative 4 plus 2 is negative 2, and the sign of negative 2 is negative. So I put a minus sign right there. What this means is that for all the numbers between negative infinity and negative 2, you plug them into this x plus 2, the sign of that number is going to be negative. I do the same thing with x minus 1 for this cell. And if I choose any number between negative infinity and negative 2, plug it in here, I will get a negative sign. And likewise, I'll get a negative sign for x minus 3. All right, so I have 3 negative signs. So what is that telling me? Well, that tells me if I choose any number between negative infinity and negative 2, and I plug it into f of x, I will have a product of 2 negative numbers divided by a negative number. And whenever you multiply 2 negative numbers and divide it by a negative number, the result is negative. Okay? So this is the information we're looking for right here. What does this tell us? That means for any number between negative infinity and negative 2, f of x will have a negative sign. And that means that it will be below the x-axis on this interval. So in your sketch of this function, your drawing had better show the f of x being below the x-axis on this interval. And then we repeat the exercise for the remaining 9 cells. So now we choose the interval between negative 2 and negative 1. So choose a number between negative 2 and 1. Choose a number between negative 2 and 1. So if I choose a number between negative 2 and 1 and I plug it in for x here, that factor will contribute it positively to f of x. Choose a number between negative 2 and 1, plug it in for x for this factor, and that will still make the factor appear as negative, and this likewise, this factor will be negative. So what this is telling me is if I choose any number between -2 and 1, and I plug it in for f of x, I will be multiplying a positive number by a negative number and dividing by a negative number. And whenever you do that, you have a positive result. So this tells me between -2 and 1, f of x is above the x-axis. Okay? And so when you in your sketch, you'll need to show your drawing as being above the x-axis. All right, so 6 more cells to go. I answer the same question. Pick a number between 1 and 3 and plug it in for x and x plus 2. And when you do so, you'll get a positive result. Pick a number between 1 and 3, plug it into x minus 1, and you'll get a positive result. Likewise, if you pick a number between 1 and 3 and you plug it into x minus 3, you'll get a negative result. What this is telling us is if you choose a number between 1 and 3, plug it into f of x, you will have a product of 2 positive numbers divided by a negative number, and that is always negative. And so on this interval from 1 to 3, f of x is below the x-axis. And so your drawing had better demonstrate that. All right, so now we go for x greater than 3. And of course, when x is greater than 3, all of the factors will exhibit positive signs. And f of x is positive, and so you're above. Okay, so above. So there you have it. So there's your table of signs. And it tells you which direction in which to draw your graph. So now we have all 6 steps filled out, and we're ready to construct our graph. So next page, insert the graph, insert graph, and say between, there we go, next. 1 second. Okay, so let me establish the grid. What we're graphing now is, oops, yellow's kind of hard to see, is it? Let me try a different color. Let's try blue. F of x is equal to, what was our function? X squared plus x minus 2. Over x minus 3. All right, so we're going to sketch that using the results from the 6 steps. Okay, so now, what did we have? We had a y-intercept at, what was it, at 0, 2/3. Y-intercept at 0, 2/3, so roughly there. I think I may have miscalculated the intercept in my previous calculation, so please go back to the notes. Let me see if I can. Is it here? I may have deleted it. So I think I may have made a mistake on the y-intercept. Yeah, that slide is now missing. So I may have misspoken on that. Well, anyhow, please check my work. The y-intercept should be at 0, 2/3. The x-intercepts we had to be at 1, 0 and at -2, 0. Okay, so there are our intercepts. And then we had a vertical intercept at x equals 3, right? So x equals 3 is a vertical intercept, which I'll draw as a dashed vertical line. And then we had a slant asymptote, y is equal to x plus 4. So I'll write that as for your reference. We want to graph this as a dashed line. Y is equal to x plus 4. right? So we have a slant asymptote there. And so if x is 0, y is 4. And if x is -4, y is 0. So we just use those 2 points to quickly plot the slant asymptote. Okay, so here's our slant asymptote right there. All right. Okay, so here we have it. All right, now, so we know using our table of signs right here, using this information, we know that the graph for x less than 2 is below the x-axis. See right here, this information right here tells us for x less than -2, f of x will be below the x-axis. And it has to be asymptotic to the slant asymptote. So if we were to draw that, we'll draw it in red, this piece, it's going to look something like this. Okay, see how, oops, it should be kind of asymptotic. I'm not sure why I curled it like that. So let me just erase this. Draw back in my slant asymptote right there. So there's what it would look like for x less than -2. See how it's below and asymptotic to the slant asymptote? Now between 2 and 1, we know that the graph is above the x-axis. And it has to connect the dots. So the only kind of picture that can do that would be a shape that's like this. The 3 dots are connected and it's above the x-axis. All right, now between 1 and 3, we know that the graph is below the x-axis. So that means that we have to go back below and we have to be asymptotic to this vertical asymptote. So that means the graph will look like that. All right, so now that leaves just one more piece of the picture, and that is what is the graph consisting of for x greater than 3? All right, so x greater than 3, what happens there? Well, it appears as though we have a couple of choices. We can put stuff here, or we can put stuff here. So which is it? Okay, well, obviously it can't be this part right here, because if we were to put stuff here, note that this branch, this black branch, would drop below the x-axis, and we know that the graph is above the x-axis for x greater than 3. So it cannot be this piece right here. So this is wrong. Okay, so let me erase that piece. For the simple fact is that it drops below the x-axis. So erase, erase, erase. So this is the piece that we would use right here, this branch right up here. All right, so now, okay, so there we have it. So there's our graph. So there is one more issue that we want to deal with, and you see this branch right here? It happens to have a local minimum. Why is that? Because supposing that this little red dot right there is the local minimum, we note that for values of x between 3 and the abscissa of this local minimum, the graph is decreasing. Okay, and then for values of x greater than the abscissa of the local minimum, the function is increasing like that. So whenever you have a transition from decreasing to increasing, you're going to have a local minimum. And what I would like for you to do is to actually calculate the coordinates of that local minimum. So how do we calculate the coordinates of that local minimum? Well, it turns out to do so, you use your favorite Math105, Math055 technique, and you build a function table. All right, so interestingly enough, we're going to build a function table for different values of x. So, and we're going to look for this transition from decreasing to increasing. So here's how we do it. We kind of guess, okay, make an educated guess as to where the local minimum happens to be. Oh, so it looks like it may happen at, say, 4.8, right? So let's say we calculate output values at 4.5, okay? 4.6, and I'm just randomly going to select some values, say 4.8. How about 5? 5.5. So this function table is used to hunt for the local minimum. 5.7, say 6, maybe 6.5, and 7. Okay, so let's fill in the function table and look for a pattern in f of x output. So let me grab my calculator. Okay, and let's figure out what the function value is at 4.5. So 4.5. So 4.5 squared plus 4.5 minus 2 is equal to that divided by 1.5. Now please check my math, okay? I contend that this output value would be 15.167. Okay, now let's try 4.6. So 4.6 squared plus 4.6 minus 2 equals that divided by 1.6. So this would be 14.85. So you see we're decreasing. As x increases, we're decreasing for f of x, which is consistent with our arrows, right? Now 4.8. Okay, so 4.8 squared plus 4.8 minus 2 equals that divided by 1.8. So it would be 14.36. So what is f of 5? So that would be 25 plus 5 minus 2 is equal to that divided by 2. So f of 5 is 14. By the way, you can plot these points on your graph if you wish as well. So what is f of 5.5? So 5.5 squared plus 5.5 minus 2 is equal to that divided by 2.5. That would be 13.5. So we're still in decreasing mode, right? As x is increasing, f of x is decreasing. 5.7. 5.7 squared plus 5.7 minus 2 is equal to that, divided by 2.7. So that would be 13.4. Oh, getting small. Oh, well, the rate of decrease is slowing down now as we get closer to 6. So what is f of 6? So 36 plus 6 minus 2. I'm using my calculator. Divided by 3. 13.33. Yeah, so we're leveling out now. Looks like we're leveling out. And what is f of 6.5? $13.35. Aha. So we're starting to go back up. All right. See the pattern? And so I'm willing to bet that f of 7 is greater than 13.5. 49 plus 7 minus 2 divided by 4. Yes, it's 13.5 as well. So there's our level out. And just for good measure, let's do 7.5 to show that it's starting to increase. So what is f of 7.5? That would be 13.7. Yes, very good. Okay, so look at profile. Okay, we're decreasing up to say 6, and then once we get greater than 6, we start increasing. So it appears that there's a transition going on somewhere between 6 and 6.5. So the abscissa of our local min would have to be at 6.5, somewhere around 6.25, which would be right about here. So that means we need to adjust this branch a little bit, not too much. Let's call it at 6.25. So 6.25 is right about there. And let me extend my slant asymptote. And so, voila. So it's got to be shaped like that to be correct. Okay, so there we have it. So there's our graph. Now, of course, we can check our graph using the online calculator. So let's do that, and that'll be the last initiative we take for today. I'm going to finish lesson 1 in my next demonstration, next lecture. Okay, because I have several more examples I want to walk through. But anyway, as the last act of this particular video, let me go to another page, and let me insert the browser tool again. Pull up the website. Okay, plug in that. Go to the website, pull up the graphing calculator. Okay, so plug in the come on. So the numerator was x squared plus x minus 2. So put that in. Be sure to put that in parentheses. X squared plus x minus 2 divided by what? X minus 3. Oh, come on. Sorry about that. Try it again. The tools are still being perfected, so I apologize for this rather uneven display of graphics. So wait for a second for the web page to resolve. Okay. Yeah, come on, I know. Okay, try it again. So that was x squared plus x minus 2 divided by x minus 3. And we'll keep the zoom boxes the same. I won't adjust this. And so if we submit, we should see those two branches kind of at an angle, determined by the slant asymptote, right? So computing, right? And there we have it. So what's missing? Looks like we need to extend our Ymax out. So let's extend it, say, out to 20. We're missing the top branch, aren't we? So we have to adjust to get values x greater than 3, and there we have it. Okay, so here's our vertical asymptote at x equals 3. Local minimum, say, right about here. Right about there somewhere. That's about 6 1/4. And then here's the here's that part that we explained was above the x-axis. And then, interestingly, what's not drawn on this graph, of course, is the slant asymptote. So one disadvantage of this graphing tool, it doesn't show your slant asymptotes. All right, so that is it for this particular lecture. This is lesson 1. I'm going to finish lesson 1 on the next lecture. So please make sure that you go through these notes thoroughly and do the assigned homework. If you have any questions, as always, feel free